Dear friends, welcome to a lecture on complex analysis. In this lecture, we shall see the meaning of stereographic projection and Riemann sphere, and also we shall see point at infinity. Then we shall obtain some results regarding point at infinity, that means z tends to infinity. So, first we shall see what is a stereographic projection. Stereographic projection is a one-to-one correspondence between points of a sphere and plane, complex plane we shall consider, or all points of sphere are projected onto complex plane. And we shall see, for that purpose we shall consider a sphere, unit sphere passing through origin and whose equator lies in the complex plane. We will draw a figure for this. Suppose this is unit sphere, and because it is a sphere, we shall show the upper hemisphere by dark line, and the lower hemisphere we shall show by dotted line. And see, this will be equator of the sphere. This is the center, which is origin, and this is the equator of the sphere. This is the equator of the sphere, and this equator lies in the complex plane, and therefore the complex plane we shall consider here passing through the equator. This is origin, and we shall draw a complex plane, see, like this. Bigger plane we will have. This is suppose the complex plane, and you imagine this is a sphere, hollow sphere, and its upper surface is above the plane and lower surface, that is southern hemisphere, is below the plane. And now we will have this as its north pole. N is the north pole, and because the sphere is of radius 1, we will denote the coordinates of north pole by 0, 0, 1. Now this is the south pole, and this is complex plane, z plane. Now for every point in the complex plane, there we draw a line passing through the north pole, and that line will be like this. Suppose this is a point z. So, we will consider this as a point z is here. Then we have to draw a line passing through this point z and joining this north pole N. Like this, and let this point be P. It cuts the sphere on the surface of sphere at point P, and then it further meets the north pole N. So, we have to imagine this, and this is the hidden part of the line shown by dotted line part, and if this is Z. Similarly, if you consider another point as say Z1, or that point may be taken here or anywhere, then it will join the north pole. And see, on the surface of the sphere, this is the point, say P1, and this is the point Z1. Likewise, if you consider this point as Z2 and join this to the north pole, then it will be like this, Z2. This point is P2. So, for every point on this plane, there corresponds to a point on the sphere. if this is Z3, we may draw line passing through Z3 and joining the north pole, and this is P3 and so on. So, thus corresponding to every point the Z in the plane, there is a point on the sphere which meets the line joining the point and the north pole. So, this is the point P3, and as we move farther, see if this point is considered, then the point on the sphere will approach towards the north pole. So, this will be the point, say if this point is P, I shall write here, and then this will be the point here as suppose Z4, and this is the point P4 and so on. So, this is actually joining, the line is passing through north pole, and then the point will be like this Z4. So, thus every point on the plane, there corresponds a point on the sphere, and similarly for every corresponding point on the sphere, there corresponds a point Z in the plane, and therefore, this establishes a one-to-one correspondence between the points of sphere and points of the complex plane. Now, what happens if this equation of this equator is mod Z is equal to 1, all the points on the equator are mapped to itself, point of sphere and the point on the this equator are mapped onto each other. And but what about the point inside this? The point inside this will be mapped to southern hemisphere. That means, if you consider this point as say Z5, then join this point Z5 to north pole, and it will intersect this southern hemisphere at point P5. So, the points inside this equator, or that means mod Z less than 1, the points will be mapped on to southern hemisphere. And see the point on the equator, mod Z is equal to 1, the points lie on equator of sphere, and mod Z greater than 1, the points will be mapped on northern hemisphere. So, in this way all the points will be mapped, but see the north pole N is associated with the point at infinity, and that means this north pole, a line passing through north pole only, and that will be like this, and this will be associated with a point at infinity. So, here also this point will approach towards infinity, and so because this will not cut the sphere in other point, it is the only point N, and the points at infinity are associated with this N, and in this way there is a one-to-one correspondence between the sphere and the extended complex plane. The complex plane with point at infinity is called extended complex plane. And therefore, there is one-to-one correspondence between the points of sphere and the extended complex plane. This correspondence is known as stereographic projection. That means we have projected sphere onto a plane, and that type of projection is called stereographic projection, and the sphere is known as Riemann sphere. The sphere, the unit sphere whose center is at origin and the equator lies in complex plane is called the Riemann sphere. Here is the north pole which lies on the z axis, x axis and y axis will be like this, which is in plane, the complex plane. The sphere is known as Riemann sphere. So, this is the meaning of stereographic projection and Riemann sphere. Now, we shall consider some results regarding point at infinity. Here we have introduced the point at infinity, which is associated with, in this stereographic projection, which is associated with the north pole, because as the points move away, the point on the sphere, corresponding point on the sphere will approach towards the north pole n. Now, we shall consider some results. I have written here as a theorem, if the result as a theorem, if z naught and w naught are points in z and w plane respectively, then the first result states limit z tends to z naught of f of z is equal to infinity if and only if limit z tends to z naught of 1 over f of z is equal to 0, and so on. Now, we shall see what is again the meaning of z tends to infinity. Earlier we have seen in stereographic projection, the point at infinity, the north is associated with the north pole, and that means the point moves farther from the origin. If the point moves farther from the origin, then mod z becomes greater and greater, that is, this is bigger and bigger, is greater than some number m, whatsoever it may be, large, and then we say this z approaches towards infinity, or that means we can say z approaches infinity if for every small positive number epsilon, we have absolute value of z is greater than 1 upon epsilon, then we say z approaches infinity, because absolute value of epsilon is a very small number, then 1 upon epsilon will become bigger. So, as we make epsilon smaller and smaller, 1 by epsilon will become bigger and bigger, and that means here z will approach towards infinity. For example, if epsilon is 0.1, then 1 over epsilon will be 10. If epsilon is 0.01, 1 over epsilon will be 100, and so on. As epsilon becomes smaller and smaller, 1 by epsilon becomes greater and greater, and that means 1 upon epsilon will approach towards infinity, or otherwise we say z approaches to infinity. So, this is this condition we shall use for z approaching infinity or any other point z not approaching infinity. Now, the first result we shall prove as like this. Proof for first, and we will use the definition of limit to prove these results. Let z tends to z naught, assume this, let limit z tends to z naught of f of z is equal to infinity. Then what this will give, and this is known as epsilon neighborhood of infinity. Here this mod z greater than 1 upon epsilon is known as epsilon neighborhood of infinity. Now, here what is there, that f of z approaches infinity, and therefore, here instead of mod z we will have mod f of z, and that will be greater than 1 upon epsilon. Then by definition of limit, and limit at infinity also, for every small positive number epsilon, however small it may be, there exists a positive number delta, epsilon delta definition we are using, such that, and see what we will write is f of z, it approaches infinity, means absolute value of f of z is greater than 1 over epsilon. Z approaches infinity means absolute value of z is greater than 1 upon epsilon for every positive number epsilon, and whenever here z approaches z naught, means we have to consider the delta neighborhood of z naught, whenever 0 is less than z minus z naught is less than delta. So, this is the definition of limit we have used here, and you note here we should not write f z minus infinity less than epsilon, but we should write whenever the limit is at infinity, we have to write this in epsilon neighborhood of infinity, mod of f of z is greater than 1 over epsilon. And now, this can be written as, we want to show this limit of 1 by f of z, and therefore, we shall take the reciprocal of this, taking reciprocal of only the first inequality. So, taking reciprocal first inequality. So, what we can write is, if you take the reciprocal, the inequality reverses, and we have mod f of 1 upon f of z, mod 1 upon f of z, that is reciprocal of f of mod f z, and is this inequality greater than becomes less than, reciprocal of 1 upon epsilon is epsilon, and thus this is the same, this implies this one, and this condition we shall keep as it is whenever 0 is less than mod z minus z naught is less than delta. And now, see what this implies, or further we can write this as, that is absolute value of 1 upon f of z minus 0 is less than epsilon whenever 0 is less than mod z minus z naught is less than delta. And what this implies? This implies limit of 1 over f z is equal to 0 as z approaches z naught. So, this is what we wanted to prove, and that is limit z tends to z naught of 1 upon f of z is equal to 0, and so this is what we have obtained. And thus, limit, if limit of z f of z as z tends to z naught is infinity, then we get limit z tends to z naught, limit is the same, reciprocal of f of z is equal to 0. And now, the result is easy to verify, or we shall consider an example for this one as, for example. But what about the condition is if and only if the converse part will be obtained, or the proof of the converse part will be written accordingly as by writing the reverse steps. So, start with this limit f of z is 0, then we can write this step, and then we can write this one and take reciprocal of the first inequality, we will get the first result. So, starting second result we can obtain the first result. The converse part can be proved similarly. Can be proved in similar way. and thus or similar manner. In writing the steps in reverse way. So, now we shall consider an example to understand this result. So, what we will have is limit 1 upon f of z is 0 and this limit is infinity. So, limit example, for example, we will have to consider limit z tends to say suppose 2 and we want to take it as 3z plus I divided by z minus 2. How to obtain this limit? So, to get this limit we may take the limit of the reciprocal and see what is 1 upon f of z, this is f of z. So, we have limit z tends to 2, 1 upon f of z means z minus 2 divided by 3z plus I, and this is simple to verify. If z tends to 2, 2 minus 2 is 0, 0 divided by something which is non-zero, and 0 divided by a non-zero quantity is 0. So, therefore, this is 0, and because this limit is 0, this limit must be infinity, and therefore, this is equal to infinity since. So, this is 0, and thus these results are useful to obtain the limits, or we can show this as infinity because the limit of the reciprocal of this f of z is 0, and therefore, this is infinity. Now, we consider the second result, proof for the second result. Proof of 2. See what is this we shall again show that the first statement implies the second statement. Consider this limit z tends to infinity. Let limit z tends to infinity of f of z is equal to w naught, and thus what this implies, given epsilon greater than 0, for every epsilon greater than 0, therefore, for every positive number epsilon, or in short it is written as epsilon greater than 0, where epsilon is real number positive, and but we are writing a for every positive number epsilon there exists delta, positive number delta, real number, positive real number delta, such that now we are applying the definition of limit for this, such that mod of f of z minus w naught is less than epsilon whenever. Now, here z is tending towards infinity, and when z tends to infinity we have mod z is greater than 1 upon epsilon, but epsilon is used here and we have written there exists delta. So, we use here delta to show z tends to infinity, mod z is greater than 1 over delta. See, z approaches infinity means mod z will be greater than 1 upon a positive small positive quantity, and here instead of epsilon we have used delta neighborhood at infinity. So, this is the result that we have, and from this what we have to prove is limit regarding 1 by z, and therefore, we replace z by 1 by z in this result, replacing z by 1 over z we get. So, this is true for every z, true for 1 upon z, and what we will get is mod f of z, f of 1 upon z, absolute value of f of 1 by z minus w naught is less than epsilon whenever 1 by z, mod of 1 by z is greater than 1 upon delta. And now you see this is this only we can write as, and here, that is mod of f of 1 by z minus w naught is less than epsilon whenever, and take the reciprocal of this, taking reciprocal of second inequality. If you take the reciprocal, it becomes mod z, and this is less than 1 upon delta, reciprocal is delta, and obviously 0 is z is not 0 because we are taking reciprocal, z is not 0, 0 less than mod z is less than delta, and this may also be written as see, I shall write here. Only we can write this mod z as z minus 0, or which is the same, that is modulus of f of 1 by z minus w naught is less than epsilon whenever 0 less than mod z minus 0 is less than delta. See, mod z I have written mod z minus 0. Why? Because now this is to be written in the form of limit. So, thus that is, this is limit z tends to 0 by definition of limit. This is neighborhood of 0, z lies in the neighborhood of 0, delta neighborhood of 0 means z is close to 0, and f of z, f of 1 upon z, this will approach towards w naught. See, this is what we want to prove, this one, limit z tends to 0, f of 1 by z is equal to w naught, and thus starting with the first result we have obtained the second. The converse part is proved similarly. We get the converse part in similar manner. And now we will have one example of this second result. So, consider example for second. So, what is this limit as z tends to infinity is w naught, and we will have limit z tends to infinity, say 3 z, or yes, 3 z plus 5i divided by 2 z minus 4, and we want to obtain this limit as limit z tends to infinity, and for that purpose what we shall obtain is limit z tends to 0 of f of 1 by z, and here f of z is this one. So, here f of z is 3 z plus 5i and 2 z minus 4, and therefore now limit z tends to 0 of f of 1 by z is equal to limit z tends to 0 of f of 1 over z means replace z by 1 upon z, and this will be 3 upon z plus 5i as it is. Wherever z is there, we have to write 1 by z. So, this is 3 by z plus 5i, and this is 2 by z minus 4, and to get this limit, see, this limit is to be evaluated as limit z tends to 0, multiply the numerator and denominator by z, see here, and therefore if you multiply the numerator and denominator by z, we will get this as 3 plus 5i into z divided by, at the denominator multiply by z, we will get 2 minus 4z, and as now z tends to 0, so this is 0, this is 0, and this limit becomes 3 by 2. So, that means limit z tends to 0 of f of 1 by z is 3 by 2, and therefore, this limit z tends to infinity of f of z will also be 3 by 2. Since, so this is the application of the second result. To get limit at infinity, we have obtained the limit at 0 of, but of which function, f of 1 upon z. So, and that if it is w naught, then that is the limit of the first. Now what about the third result? Third result we shall prove, and it is also easy to prove. Let limit z tends to infinity of f of z is equal to infinity, and here both approaches infinity. The point approaches infinity and f of z are also approaching towards infinity, and therefore according to this definition, for every epsilon, every positive number epsilon, so however small it may be, positive number epsilon, there exists for every small positive number epsilon, there exists a small positive number delta, such that this f of z, absolute value of f of z is greater than 1 over epsilon, and epsilon neighborhood we have used. Whenever z also approaches infinity, therefore we have mod of z is greater than 1 over delta. So, the same definition is used, z tends to infinity, and here f z tends to infinity means mod f z is greater than 1 upon epsilon. Now, we shall take the reciprocal of this, taking reciprocal of this statement, both inequalities, taking reciprocal. See, the inequality reverses, we get this as we want to take this as limit of this f of 1 by z, and therefore before taking reciprocal we will replace z by 1 upon z. So, replacing z by 1 upon z, z by 1 by z. See, what we shall get is, and when we replace z by 1 upon z, the inequalities will not change, only z is to be replaced by 1 upon z. So, it is a mod of f of 1 by z, and that is greater than 1 upon epsilon, whenever mod of 1 upon z is greater than 1 upon delta. And now we will take reciprocal. So, taking reciprocal, what we shall get is, this is 1 upon mod see f of, or absolute value of 1 upon f of 1 by z, absolute value of 1 upon f of 1 by z is less than epsilon, whenever absolute value of z is less than delta, or the same thing we can write as, that is absolute value of 1 upon f of 1 by z minus 0 is less than epsilon, whenever 0 is less than z minus 0 is less than delta. This is deleted neighborhood of delta 0 of 0, and thus this implies limit as z tends to 0 of this 1 upon f of 1 by z is equal to 0. So, this is what we wanted to prove, and thus the converse part will follow in the similar manner. And now we will have one example to verify this, or as an application of this result. See, we will write like this, limit z tends to infinity of, say, 4 z raised to 4 minus I divided by 3 z cube plus 5. We want to find out this, and to obtain this result we shall obtain limit of 1 upon f of z. Here what is f of z? F of z is see 4z power 4 minus I divided by 3z cube plus 5, and therefore what will be f of 1 upon z, replace z by 1 by z. So, it is 4 by z raised to 4 minus I, only z is to be replaced by 1 by z, and this is 3 divided by z cube plus 5. This is f of 1 by z, and if you multiply this by the numerator and denominator by z power 4, then this will be 4 minus I into z power 4 divided by, and if you multiply it by z raised to 4, then this becomes 3z plus 5 z power 4. This will be the result, and this is 1 by z, and here we want to put z is equal to 0. But you see what will happen if we want to take this as z approaches towards infinity. We have to take the reciprocal of this, 1 over 1 by f of 1 by z, and therefore limit z tends to 0, 1 upon f of 1 by z is equal to limit z tends to 0, and reciprocal of this will be 3z plus 5z raised to 4 divided by 4 minus I into z power 4, and obviously this will become 0 because the denominator is non-zero, denominator will be 4 minus 0, but the numerator is 0, and therefore this is 0, and thus this limit is equal to 0. This limit is we have obtained, because we have obtained limit of z tends to 0, 1 over f of 1 by z is w naught means 0, and therefore this limit is also 0. We may write the reason here as since. So, thus these results are useful to obtain the limit at infinity, and in this lecture we have seen first stereographic projection, and then we have proved this theorem. I hope you will understand this. Thank you for watching the lecture.